Okay, so this is going to be a couple force vibration questions and a damping question because I can. I do think that it's important to do damping questions, but not to do a forced vibrations problem with damping. It just seemed to work out reasonably well to do 3 examples at a time. There was another video that I've done looking at sort of increasing complexity of a free vibration, damp vibration, but I didn't look at force vibration. So this video does that. Again, I'm going to have one problem, and it's to sort of look at these rigid body problems, and again, play with definition. Number one thing is it's all second law. This is a second law set of problems, and you really need to be comfortable applying the balance equations for second law. So here we have sort of a complex motion. I've got a mass on a cart, which is 2m, an external force which is applied at F naught sine omega AT, and what omega A will cause excessively large oscillations of the system. So I've got all that together. And I've got all of that together, and if I look at the problem, I've got kx plus x static. That's the normal way to write this. I've got normal force, I've got the weight force, and I've got 2t because there's 2 wraparound lengths of the cable. On the other side, I have the forcing frequency, which is down here. And I have the weight, which is going to kind of not play a role too much. And I've got tension. So if I write this all out, I can sort of get rid of the weight because it's going to be eliminated when I look at the spring force. And that's my static equilibrium terms. So in terms of my expression, it looks something like this. I've got minus kx plus 2t twice mx double dot, and I've got twice f naught sine omega at minus t mx double dot. So all the terms are there. I've got that, and I've got this, and that was to sort of balance everything out. So if I do that and do all of the sort of manipulations, I end up with this expression right here, which is that x double dot plus k over 6m x 1/3 m 1 over 3m f naught sine omega at. So I got rid of the t in that expression. And really, I think this term goes away. So I've got k over 6m, which is my normal or acceleration. And the omega a that I don't want to achieve is the same one as omega n, which is k over 6m square rooted, which is 1 hertz. There you go. Not so bad. Similar problem. What is the equation of motion for the mass which is subjected to a suddenly applied force F naught of 100 newtons that remains constant after application? So this is a little bit different. There's no time variance. Displacement and velocity of the mass are both 0 at time equals 0. So here's sort of the free body diagram. Everything's there. I don't have any weight force because it's horizontal. Everything's sort of lined up. And I get the standard expression, which should be k over mx right there. X double dot plus k over mx equals f naught. I've got a standard solution, which is going to be characteristic plus particular, and that's going to have this form right here, which is a sine omega nt, b cos omega nt plus f naught over k. So don't you need a time varying force? Well, you do normally, but this case it's treated the same way because it's just an external force that's being applied to the system. So you don't have to have a time varying force in these problems. You just have to have an external force applied. So normally we get rid of them if there were internal, say for example a weight force, but we can't do it in this particular case. So substitute in terms all of the expression, and we end up with x equals f naught over k, 1 minus cos omega nt, or based on the value of k and m, 1 minus cos square root t. That was cos square root 10t. Excuse me. This is not a force vibration problem. It's just one that I kind of like to do just on principle. It's nice to look at a rigid body problem where you have, say, a system which consists of a uniform rod that sort of travels along here, which has a spring over here with K, and C, which is over here. A and B are given here, and we have all these terms. A, B, there's the spring force acting downward and the damping force acting downward. You'll notice over here I've gone back to my standard definition. Counterclockwise is positive, x and y are positive in the right and upward direction respectively. So if I put in terms, I end up with minus k sine theta a cos theta minus cb cos theta theta dot b cos theta, lots of mess. But then I can sort of say, well, this term right here for very small displacements, cos theta is equal to 1 and sine theta equals to theta. So in that case, I end up with this expression, this next expression down, theta double dot plus 3cm theta dot 3a squared over b squared k over m theta equals 0. And that right here is my omega squared term. So again, it's not k over m, it's the force balance, or the moment balance in this particular case, of the system. And then the square root of that is 3a squared k over b squared m. C is equal to 2m omega n, 2m, and substituting in just terms, 3a squared k over b squared m square rooted. And the damping ratio you can find from the text is 3c over 2m, b squared over m, 3a squared k, cb over 2a, 3km. This is part of the standard definition. You need to have this or understand that in order to sort of extract out all of these relationships. It's c over cc. So after all of this and getting all the results, let's put in some numbers. Mass is equal to 100 kilograms. K is equal to 213 newtons per meter. A is, let's say, 1.3, and B is 2.8 meters. So the critical damping coefficient is going to be 78 newton second meters. Again, remember, all of this is Newton's second law. We give definitions and we sort of say, okay, look, C over M, K over M. But really, you need to write out the force balance, write the governing equation, then you get the terms. And you should see in each of these examples, and in the previous video also, that all of this works that way. I cannot emphasize this enough. Read carefully, draw carefully. Draw, 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 draw. And define the axes, define everything. That's going to give you the most chance of doing very well in these problems. These are not hard problems. They are hard problems if you can't visualize them.